Yeah, maybe we start and people will join.
Okay, sure. Yeah. Okay, then welcome all to the Harishchandra lecture series. Today again we have Professor Habib from SNU Noida. Today he will continue his third lecture on an introduction to Lie groups and algebras. Professor Habib.
Thank you. Yeah, so welcome back everyone. This is the third and final lecture in this sequence of giving sort of bare introduction to Lie groups and Lie algebras. So today we will look a little more at the Lie group Lie algebra relationship and spend a little more time with Lie algebras at the end. Okay, because you have to understand their workings before you can use them to understand Lie groups. Okay, so first slide as usual, we'll have a quick review of things done before. It will be very brief. So first, we have been talking about matrix groups. These are closed subgroups of the general linear group. Then we have observed that if you have such a matrix group, then the tangent space at identity is a vector space, and in fact, a Lie algebra. The Lie algebra part means that it is closed under this bracket operation, x bracket y equal xy minus yx. Okay, it's possible, there's a characterization of the Lie algebra, which matrices are actually in the tangent space. So if your matrix group is a subgroup of GL and R, then the tangent vectors would come from from n cross n matrices, and in particular, they would come from the one such that e to the tx belongs to the group for every real t. So we had that characterization in the last lecture, and we saw some applications. Another part of this characterization was that due to this, the exponential map now goes from the Lie algebra to the matrix group. And by calculating its derivative or by working directly with its power series expansion, you can see that it's a local homeomorphism at origin. Okay. As applications, we computed the Lie algebras for certain matrix groups for GLN, the special linear group SLN, orthogonal, special orthogonal, unitary. As another application of this characterization, we saw some examples of how knowledge about Lie algebra and the matrix group are connected. For instance, if the group is connected, then it is abelian if and only if the Lie algebra is abelian, which means that the bracket is identically zero. And further, if G is connected and abelian, then it turns out that we know exactly what it looks like. It's isomorphic to some torus times Euclidean space, PP cross RQ. Okay. And so in particular, if G was connected and abelian and compact, then it could only be a torus. It could be S1 cross S1 some P times. Okay. All right, so that's what we had done. And we had done one more thing, which was discussing the adjoint map, but I'll bring it up later in today's lecture. Okay. Now, okay. So now let's take a look at Lie algebra and some basic terms involving them. Let me remind you what a Lie algebra is. It's a vector space with a bilinear map, which we denote by this bracket with two properties. X bracket X should always be zero. This is called antisymmetry. And there's a sort of relationship, So what happens is our main example of Lie algebra is when you look at square matrices and take xy minus yx. That is, of course, not associative, but it has another property which kind of fills in for associativity in some ways. It's called the Jacobi identity, and that is what I have written here. Okay, and you can see the pattern. If I bracket x with yz, okay, and then I sort of cyclically permute. I send z to the x position, x to the y position, y to the z position. That gives me the second term. I repeat this once more to get the third term, and all these add up to zero. So this is called the Jacobi identity. So what are examples of Lie algebras that we will already seen some, so we'll list them again. But also note that the anti-symmetry property xx equals 0, if you apply it to x plus y, that being 0, then the xx and yy terms are 0, and so you get xy plus yx equal to 0, and that gives you xy equal to minus yx. Okay? So that's another reason why this is called anti-symmetry. Okay, so our main example is, of course, you look at n cross n matrices with xy minus yx as the bracket. Then you have various subspaces which are closed under this bracket, so they also become the algebras. We saw a few of those in the last lecture. The trace zero matrices and the skew symmetric matrices were two of them. We also saw the complex matrices, the skew Hermitian matrices. They are also an example of Lie algebra. Yeah. Okay, and there's another example which we have known since school. Right, you look at R3 and you take the vector cross product, and that cross product also has the right properties and makes R3 into a Lie algebra. That's actually quite a useful Lie algebra as well in the theory. Okay. All right, some terms, So G is abelian if the bracket is identically 0. Okay, that's your definition of an abelian Lie algebra. All right, what should be a Lie subalgebra? Of course, so an algebra is a vector space with a bracket, so a subalgebra has to be the same thing. And therefore, first of all, this H needs to be a vector subspace of the Lie algebra G. And second, it should be closed under the bracket. So if X and Y belong to H, then the bracket belongs to H. So that's the definition of a Lie subalgebra. And on the previous slide, SLN, ON, UN, these are all Lie subalgebras of MN. Okay. Then we also have a definition of ideal. Okay. So what's an ideal? Again, it should be a vector subspace of G. But now the bracket requirement is stronger. You can probably guess what it is. If I take something from H and I take something from the big algebra, then the bracket should be in H. Right? So usual definition of ideal for a ring. Okay. All right, so that's the definition of an ideal. Then we have homomorphisms. Okay. So there are two structures, vector space and bracket. The homomorphism needs to preserve both of them. So it's a homomorphism if it is linear, first of all. Second, it should preserve the bracket. So phi of xy. Okay. The bracket should be the bracket of phi x and phi y. Okay. All right. So these are some standard terms defined in the obvious ways. Okay. Now, if you have a Lie algebra homomorphism, then we look at the kernel and the image. Okay. And it would be easy to see that both of them are Lie subalgebras. So image of phi will be a Lie subalgebra of H. Kernel of phi would be a Lie subalgebra of G, but actually it turns out to be strong. To be more than that, it actually turns out to be an ideal. Okay. So again, these are very routine, easy to check things and expected also. Kind of ideas, it's like subalgebras work like subgroups, ideas work like normal subgroups. And it's not just rough patterns. There's also a close relationship because the because of the Lie group Lie algebra relationship. And remember that the bracket came by differentiating conjugation, right? So that is one reason why there will be a strong relationship between being normal and bracket properties. Okay. Okay, now ask you to recall, I will recall it for you, something from the second lecture, the very end of the second lecture. I defined this map called the adjoint map, written with a capital A. This is a map from the matrix group to the automorphisms of its Lie algebra. These are vector space automorphisms. Okay. Defined by that add of some G. Okay, what automorphism is it? So I have to say what it does to some member X of G, and it gives you G times X times G inverse. We already saw that the Lie algebra is closed under this operation. And then one checks that add of GH is add G composed with add H. So this add is a homomorphism, group homomorphism from G to the invertible linear maps on the Lie algebra. Okay. Okay. Now, once you have such a map, you can talk about its derivative, and the derivative goes from the tangent space to the tangent space. So the tangent space are the relevant Lie algebras, little g, and all the linear maps of little g. And how do you differentiate? The derivative acting on a tangent vector is just the directional derivative in the direction given by that tangent vector. So here we are differentiating at identity, right? And what does, right? So the map, the derivative applied to x is going to be a member of ng. So it's going to be a linear map. So I have to say what it does to some y. So that is why the left-hand side is the add of x acting on y. This will just be the partial derivative in the x direction of add, and then that acting on y. So just write down the definition of partial derivative. You need a curve in the x direction, that is exponential tx. To differentiate along that, and we have already seen that this is the bracket of x with y. That's also something we saw in the first lecture. Okay. All right. So when you differentiate the adjoint map, the answer is very simple. Okay. You are simply bracketing with x. Okay. So for any Lie algebra, we can do this. We can fix an element x, okay, and define a map by bracketing this x with any y that is put in front of us. So we define these maps. So given any x in the Lie algebra, we define a map add x, which takes y to bracket of xy. Because the bracket is linear, bilinear, this map is linear in y. Okay. So this creates a bunch of linear maps add x. Okay. And so I get a map add. Now this is a right. This is with little a, and this add goes from the Lie algebra to the invertible. To all the linear maps on the Lie algebra. Okay. And one can check that this map, little add, is a Lie algebra homomorphism. That means I need to check that add of xy, this is going to be a linear map. It needs to be bracket of add x, add y. Okay. Okay. So I have to apply both sides to some z and see if these two linear maps are the same. Let me create some space so I can do that. Okay, so these are two linear maps, right? We want to check they are the same. That means we should apply them to some z and see what happens. Well, if you expand this and see, you find that you end up with the terms of the Jacobi identity. And therefore this is correct. Okay, this is an exact match with the Jacobi identity if you just write everything out. Okay, and so this thing holds, and this map little ad becomes a Lie algebra homomorphism. Okay, and so what we have seen is that if you start, with the original ad with the capital A, I don't know, this notation is okay to write but difficult to speak. Okay, so we have two ad maps, one with capital A, one with little a. The one with capital A is at the group level. Right? So it's a group homomorphism from the matrix group to the invertible linear maps on the Lie algebra. Then you have the little ad, which is a Lie algebra homomorphism from the Lie algebra G to all the linear maps on G. Okay. And what we saw here on this slide is that when you differentiate capital ad, you get little ad, right? So this uh, homomorphism at the group level by differentiating induces a homomorphism at the Lie algebra level. Okay. So let's see. Okay, here we have just listed both things. You have capital ad at the group level, you have little ad at the Lie algebra level. And then remember, I have maps going like this from the Lie algebras to the group, right? These are the exponential maps in each context. Okay. So the two rows are connected by these vertical exponential maps. And naturally, we would like the maps to be compatible with each other, and that turns out to be true. So what happens is this diagram commutes. Okay, meaning that if I start with some x in the Lie algebra and first I take little ad of that, and then I take exponential. Okay, so these addx's are linear maps, and we have defined what is exponential of a linear map. Right? Then we should get the same thing as first taking the exponential to get into this group. Okay, and then applying capital ad. Okay, so this should happen. Anyway, we are claiming that this happens. All right, let's do this proof. It's a proof of the similar kind that we have been doing. We just prove things by differentiating what's happening at the group level to move to the algebra. Okay, so what will we do? We will fix an x in the algebra. We want to study, one of these terms. So start with one of them, start with capital ad of e to the x, but put a t with the x. So now I have a function sigma t ad of etx, right? So this is a function from real numbers into GLG, into this matrix group. Okay. All right. And then let's see what happens when we differentiate it. Okay. So what happens if I differentiate this and let that act on some y, right? Because these are linear maps. So to see what they really are, I have to have them act on some. All right. So we will differentiate. And I'm not only differentiating at 0, it's a general. Okay, so we'll differentiate the sigma ty, which means I'll differentiate add etxy. Then you have to remember what is this add? It is conjugation. So this is etxy e minus tx. Okay. And so you apply product rule and differentiate. So when you differentiate etx and x comes down, and when you differentiate e minus tx, a minus x comes down. I can put it either before the exponential or after the exponential, because anyway the two commute. So I've got this. Okay. Now you see what this is. This is x bracketed with this term. right? This is the same in both. And what is this? This is add ETX applied to Y. And therefore, this whole thing is add of X, little add of X, composed with capital add ETX acting on Y, right? You start with Y, you apply this function, and you compose it with add of X. Okay? But this was actually the sigma t, right? This add ETX. And therefore, what we have got is that sigma dot t is add X composed with sigma t. And also, let's note what is sigma 0. Okay, it's add E0, so that's identity. So this is identity. And we have seen earlier that if you have this sigma dot t and a vector and sigma t, if something is satisfying this differential equation, then it has to be an exponential. This, okay, that's from the power series definition of exponential. So this tells me that sigma t has to be, okay, what happened here? Yeah. Right. So it's exponential and what t times whatever was the constant. So t times add x. Okay. And therefore, if you in particular take t equal to 1, right, sigma 1 is add of etx. And on the other hand, you have exponential of. Okay. All right, so that's a very familiar looking proof. I hope this must be the nth one that we have done in this way by just differentiating things involving exponential, and that helps us discover relationships. So basically, in the basic theory, one just keeps doing this sort of calculation over and over again. And I will give you some applications of this, okay, of this commuting diagram relationship between capital add and little add. I won't do the proofs today uh, because they're all very similar to the one that we just did. So I mean, it's just those one or two ideas. You conjugate, you differentiate, you get the right viewpoint and differentiate, and you are done. So let's just see what else happens with similar proofs. Okay. So here's the first thing, that suppose you had a connected matrix group and you had a closed subgroup. So then that would also be a matrix group. And suppose that was connected. Okay. And then I want to know whether H is a normal subgroup of G or not. And the answer is that this is an exact correspondence with whether the Lie algebra of H is an ideal of the Lie algebra of G or not. Okay. So normality of the subgroup corresponds to the Lie subalgebra, the Lie algebra of being an ideal. Okay? And it goes both ways. So in going from H being normal to the Lie algebra being an ideal, you simply differentiate conjugation, and because the Lie bracket is the derivative of conjugation, you get your result. To go back, you use that commuting diagram to move from the algebra to the group. And you need the connected group because what it does is it tells you that things are working out in terms of anything that looks like e to the x. But if everything is connected, then those terms are generating the groups. And so you get the results for all the elements. Okay, so that sort of is the idea of the proof. Okay, it's not difficult to execute. And so I'm just providing the statement. Okay, and so there are many similar things. For example, you could look at commutator subgroups, you could look at normalizers and so forth, centralizers, normalizers, everything. And I'll again just list a few of the basic results which are obtainable by similar means. So first, the commutator subgroup, I'm denoting by G comma G. These are generated. This is generated by all the commutators, A, B, A inverse, B inverse. So similarly, to define the commutator subalgebra, Okay, as the subalgebra generated by the brackets. But when you look at that definition and you incorporate the Jacobi identity, it turns out that all you need is the vector subspace spanned by the brackets, by all things of the form x bracket xy. It automatically becomes a subalgebra. Okay. Okay. There's a commutator subgroup and the commutator subalgebra, and the result is the expected one that if you take uh, so I mean okay, one thing is maybe not obvious from our kind of tool, but anyway, so what happens if G is connected, the commutator subgroup is connected, and moreover, its Lie algebra is the commutator subalgebra of the full Lie algebra. Okay, so that's one relationship. Then we can look at centralizers. Uh, and here there are various combinations we can look at. You can look purely at the group level, purely at the algebra level, and you can look at the group interacting with the algebra through the capital add map. Okay. So we define certain things. Given a subset of the group, I mean, you have its usual centralizer in the group. Every group, the group elements that commute with every element of A. You can also talk of group elements commuting with the Lie algebra elements in the sense that if that joint map, which is conjugation, leaves them stationary, right? Gx inverse equal to x means Gx equal xt. So you define the centralizer in the group, in the centralizer of a subset of Lie algebra, but the centralizer is in the group, okay? And so that's the second row. All the C's in the group such that add C of x is equal to x. And you can just reverse this viewpoint and you can talk of this, right? I mean, the group is interacting with the algebra, or the algebra is interacting with the group. So you can also say, what are the elements in the algebra which are not moved by some subset of the group? And you can call that the centralizer in the algebra of those group elements. And finally, you can have it purely at the algebra level. So what is the centralizer of some subset? Every Lie algebra element whose bracket with it is 0. Right? At the in Lie algebras, by commuting, we mean a 0 bracket. Okay, so I've got these four quantities. Okay. And so here are results corresponding to them. So suppose you have a subset of the group and another subset of the Lie algebra. Okay. If you take the subset of the group and look at the centralizer in the group, right? So that's a subgroup, and you can ask what is its Lie algebra, and you will get the centralizer in the Lie algebra of the same set A. Alternately, you can start with the subset of the Lie algebra, and you can take the subgroup that it's central, the corresponding centralizer subgroup of G, and you can ask what is the Lie algebra, and you will get the centralizer in the Lie algebra of that set little a. Okay. All right, so of course the two sets are the same, and you move from centralizing in the group to centralizing in the algebra. And finally, if the two sets are connected, like suppose capital A was actually a connected closed subgroup of G, and little a was its Lie algebra, then the two things would merge. The centralizer of capital A and the centralizer of little a would be the same. And the centralizers in G would be the same. But once these two are the same, then of course their Lie algebras are the same, right? So this would imply that these two centralizers also match. Okay. And finally, let's take a special case of C. So suppose my entire group G was connected, then I could take A equal to G in the third item. Okay. And it would give me that the center of G, when I take its Lie algebra, I get the center of the Lie algebra. Center of the Lie algebra means those elements of the Lie algebra whose bracket with anything is 0. Okay, okay, so there are all these nice sort of correspondences uh, between what's happening at the group level and what's happening at the Lie algebra level. And there are similar things for normalizer as well. Okay. All right. Now, this is a theorem that generalizes what happened with the adjoint maps. Remember what happened? The adjoint map was a homomorphism from the group to the algebra. From the group to GLG, and we differentiated it, and we got a Lie algebra homomorphism between the corresponding Lie algebras. And the corresponding diagram with the exponential linkages commuted. So this is saying that, well, this is actually a general pattern. Suppose you have two matrix groups, you have a differentiable homomorphism from one to the other. Then the derivative will be a linear map between the tangent spaces. And this linear map will always be a Lie algebra homomorphism, okay, between those two tangent spaces. And moreover, so now again, I'll have two rows. I have the original group homomorphism from G to H. I have the derivative. Okay, that's a Lie algebra homomorphism from the Lie algebra G to the Lie algebra H. I again put the connecting exponential maps, and we again find that this diagram commutes. Okay. And again, it's a actually very similar proof to the proof for the adjoint case. So let's skip this proof, but we see a very nice connection here, right? So we see that Lie group homomorphisms induce Lie algebra homomorphisms. Okay. And the exponential map gives you a way of going back. So that is how we can have some program where we first try to understand Lie algebras, their structure, their homomorphisms, their subalgebras, and then put that to use to discover the corresponding things for Lie groups, their subgroups, their normal subgroups, and so on, their representations. Okay. There's one very interesting fact, maybe not too important right now, but when you move to maps from a Lie group to some, say, infinite dimensional, to the linear maps on some infinite dimensional space, then this fact will become more essential. Okay, but I may as well mention it now because it's very striking. It says if you have two Lie groups, matrix groups right now for us, and you have a continuous homomorphism between them. So this phi means not just any continuous map, it needs to be a homomorphism. Then in fact, it turns out to be differentiable. So all you need is continuity to begin with, and then the differentiability after that is automatic. Okay, here some issues come up, right? So there's a correspondence. What we are seeing is that there is some sort of correspondence between Lie group homomorphisms and Lie algebra homomorphisms, right? I can go from the first to the second. So I can ask how good is this correspondence? Okay. Is it perfect? I mean, is it like a bijection that every Lie group homomorphism gives me, when it gives me a Lie algebra homomorphism, I get all possible Lie algebra homomorphisms, and different Lie group homomorphisms give different Lie algebra homomorphisms, right? Will I have a bijection? So the answer is, as usual, that things are not perfect. But there is, we have sort of partial positive results, and it's important to know them. Okay. The first one we may not be surprised by. So if G is connected, okay, and I have two homomorphisms, phi1, phi2, okay, it's differentiable G to H, such that d phi1 equal d phi2, so they're inducing the same Lie algebra homomorphism. Then at least I will have phi1 equal to phi2. Okay, and why do I need connected? Because once it's happening at the Lie algebra level, I use the exponential map and I find that it is at least happening in some neighborhood of identity. They will match there. But if the group is connected, that generates the whole group, and therefore the matching happens for all the group elements, and I get phi1 equal phi2. If the group is not connected, this need not happen. Okay. If G is not connected, then the lifts phi1 and phi2 don't have to match. At least for connected groups, this correspondence, okay, is 1-1. Right? Two things induce the same Lie algebra homomorphism. That means they were the same Lie group homomorphism to begin with. The second issue is that suppose I had a Lie algebra homomorphism, right? Was it induced by a Lie group homomorphism? Right? Every Lie group homomorphism induces a Lie algebra homomorphism. Do I get all Lie algebra homomorphisms by doing this? So again, overall the answer is no. But there is a context when the answer is yes, if G is simply connected. Okay. And you have psi G to H is a Lie algebra homomorphism, then you will have a Lie group homomorphism from G to H, right, which induces this side. Okay. And again, I mean, in some sense, hopefully this is not too surprising. I mean, you know that when things are simply connected, then lifts work. Okay. So in fact, one has to go through all that general theory to derive this. Okay. So anyway, so there's a correspondence between Lie group homomorphism, the algebra homomorphisms, and it's reasonably good. In particular, if a group was simply connected and you wanted to study its group homomorphisms to other Lie groups, then you would simply solve this problem purely at the Lie algebra level because you would know that there is a perfect correspondence between the two. And one, of course, example of a simply connected Lie group which you may have come across is SU2. Okay. As a topological space, that is just the 3-sphere. And so that is one important example of a simply connected group. And if you were studying the representations of that, you would simply move to the Lie algebra and work over there. Okay, I use the word representation right now. Sorry, habit. I need to formally introduce it. Let me do it on the very next slide. Okay. All right. So what's the representation of a group? I mean, right now, any group. Okay. So what is the word in just group theory without any other intrusion of topology or calculus or linear algebra? What is a representation? It's a homomorphism from the group to the invertible linear maps on some vector space, right? Okay. And then usually you would start putting some restrictions. So if you're working, say, with finite groups, you would restrict it to finite dimensional representations. Usually in any context, you first ask, can I at least understand things when the vector space is finite dimensional? Okay. And once you have done that, you move on to infinite dimensional vector spaces and representations into them. At which point you would probably want to add extra structure to them to make it interesting, like a norm or an inner product or whatever. Okay. So anyway, suppose the group G is a linear group. So we will follow this pattern. We first work with finite dimensional vector spaces. And generally, to keep life simpler, we work over complex numbers rather than something else. Again, that's when you first do it. Okay. But for various applications, you may want to work with other fields and so on, okay? Or even over quaternions or something like that. Okay, but at a first go, it's best to restrict to finite dimensional complex vector spaces. Okay. Now, okay. So in this context, so now for us, we restrict and are not rather than talking about arbitrary representations, we talk about differentiable homomorphisms from G to GL and C, because we want to work over complex numbers and we want to work with finite dimensional vector spaces. So that is what a representation is for us. So anyways, just a special case of a differentiable homomorphism. And such a map, right, will induce a linear map from the Lie algebra of G to the Lie algebra of GL and C, which I'm denoting by little GL and C. And these are just all the n cross n matrices. Okay. And this would be a Lie algebra homomorphism between them two, right? I mean, we have already seen that. Okay. The only issue is there's a little bit of a mismatch because this little g originally, right? When you start with a matrix group and you create its Lie algebra, that is a real vector space. But for the representation on the right-hand side, I want to work over C. So what we do is the original linear algebra that we had, which was real, we convert it to uh, a vector space that is over complex numbers. So you just expand it and make it a vector space over complex numbers, and then you work with that. So there's a little tweak that we do so just to make things convenient. So it's called complexifying the original real Lie algebra. You define GC formally as G direct sum with IG. I is just an abstract symbol, but you then define the bracket, and so now you write things as x plus iy, where x and y belong to G, and you start computing with I as if it was the complex number I. Okay. So for example, if you start with MNR and complexify, you will get MNC. So I mean, it's a very reasonable thing to do. And what happens is that your original D phi from the real space to GLNC extends to this complexification in a unique way. It extends to now a complex linear map from GC to GLNC. Okay. All right. So the original setup is over R, but it is convenient to work over C, and so we do this complexification to move from one to the other. Okay. Okay, now let me just introduce a few basic Lie algebra concepts. Okay. It'll probably be useful in later lectures for as people work with more advanced things with Lie algebras. Okay. So given any two subsets A and B of a Lie algebra, you define their bracket as the span of all the commutators xy, where x is coming from A and y is coming from B. Okay. Right. And so, for example, when is some subset of G a Lie subalgebra if its bracket with itself stays in that edge? When is it an ideal if the bracket of H with G stays in H? So this is convenient for capturing things. Now, if H1, H2 are two ideals, okay, then we find that H1 intersection H2, H1 plus H2, and H1 bracket with H2 are all ideals as well. Okay. So ideals combined with each other in any sort of way, you again get ideals. We already saw this G bracket with G, that we call it the commutator subalgebra either. Okay, and now I'm saying here are some more names for it. Sometimes people call it the commutator ideal because it is an ideal, and other people call it the derived algebra. It kind of depends on the context in which you are talking. That would determine what name you would like to use for it. Okay. And then the usual things that you have with groups and subgroups and normal subgroups, the various isomorphisms that you also have with rings, so you also have them for Lie algebras. If you have an ideal, right, then you quotient by it. Now G and H are vector spaces, so right away this quotient is a vector space. And there's a natural way to try to put a bracket on it. Right? Take the cosets x plus h, y plus h. What should be their bracket? You bracket the x and y and take that coset. And so again, routine check is that because H is an ideal, this is well defined. So you can do this, and this gives you a quotient Lie algebra G quotiented by H. Okay. And the map from G to the quotient space, which takes X to the corresponding coset, turns out to be a Lie algebra homomorphism. Okay. Right, you can define isomorphism of Lie algebras. They're isomorphic if there's a bijective uh, linear map, which is in fact a Lie algebra homomorphism. So the vector space structure and the bracket are both preserved. Okay. If you have a Lie algebra homomorphism from G to H, then remember that the kernel is an ideal and the image is a Lie subalgebra. So when the kernel is an ideal, I can quotient by it, and the quotient turns out to be isomorphic to the image and phi. Okay. All right. If you have a homomorphism from G to H and J is an ideal which is contained in the kernel of phi, okay, then your phi induces a map from G quotiented by J, right? So J doesn't cause any problems because phi was killing it. And you get a unique map from the quotient, okay, so that this diagram commutes, okay, projecting from G to the quotient and then from either the original or the quotient going to H, this diagram commutes. You have your other isomorphism theorem. Suppose you had two ideals, J and K, and J was contained in K. So you first take the quotient Lie algebra G by J. You take the quotient Lie algebra K upon J. K upon J is clearly contained in G upon J. And because K is an ideal in G, this K upon J will be an ideal in G upon J. So you can quotient them and the J's cancel and you just get G quotiented by K. Right? And the other familiar isomorphism, that if J and K are ideals, you take J plus K quotient by K, you will get J quotiented by J intersection K. So no surprises, standard results and the usual standard proofs. Okay. Okay. All right. So this is a bunch of sort of general basic stuff about Lie algebras. Okay. Let me just mention one small example that will be used a lot in subsequent lectures on Lie algebras. So let me just spend a couple of minutes in introducing it to you today. So let's look at the Lie algebra SL2C, right? This is the Lie algebra coming from the Lie group SL2C. So these are the 2 by 2 complex matrices whose trace is 0. So you can easily create a certain basis for it. Right. So, right, one is that you take a diagonal matrix 1 minus 1 and off diagonals are 0, or else you take the diagonal entries to be 0 and have, you know, off diagonal entries. So you take X with the off with 1 in the 1 2 position and Y with the 1 in the 2 1 position. Okay. All right. Now the thing is that since every Lie algebra element is a linear combination of these three, and the bracket is bilinear. So if I understand the bracket relations between these three, then in principle I have understood the bracket, overall bracket completely, right? And the bracket of anything with itself is anyway always 0, so I don't even bother to look at it. So there are three brackets that I should understand: H with X, H with Y, and X with Y. Okay. Right now that's easy to compute, right? What do you have to do? You have to take H, multiply with X, you have to multiply it in the other order, you have to subtract, you have to compute this, you have to compute this. So I won't do it. But I mean, you can see that you just multiply certain 2 by 2 matrices and you will have the result. And so let me just tell you what you get, okay? H bracketed with X turns out to be 2 times X. H bracketed with Y turns out to be minus 2 times Y. x bracketed with y turns out to be h. Okay. So in this case, I mean, the bracket relations have turned out to be pretty straightforward. Okay. And h is especially interesting. Okay, what is it doing? So suppose I looked at add of h, right? This is what happens. What does this do? You bracket anything with h, and so this will be a linear map from this Lie algebra to itself. So it will be given by a 3x3 matrix. And suppose first column I use the basis in the order hxy, right? Then what does add h look like? Well, h goes to 0, so that gives me a first column that is 0. X goes to 2x, so that gives me 0, 2, 0. And y goes to minus 2y, so that gives me 0, 0, and minus 2. So interestingly, add h has turned out to be diagonal. Okay. What about add x? Okay. So the first thing will be x bracketed with h. That will be minus 2x. Okay, that means 0, minus 2, and 0. Then it will be add x bracketed with x, all zeros. Okay. And then it will be with y. Okay. So with y, what will I get? I'm getting x with y to be h. Okay, so that gives me a 1 in the first, and then some zeros, and you can similarly find add y. Now, one thing to observe, probably a different, anyway. So this element is especially nice, right? It's acting diagonally, so how it acts on the other things is clear, and the basis is turned out to be eigenvectors of this add h. Okay. And we'll see that this will be a theme in later lectures as you try to understand certainly algebras, the simple and semi-simple one. You will first try to identify elements whose adjoint action is diagonal. Okay. Right. So, and then we will see what's happening, what are the other guys doing. So what's interesting here, maybe I should point it out. Okay, so add h, of course, yeah. So basically, let me write it as h, x, and y in this order, right? And what add h is doing is, of course, h goes to 0, so anyway, but x goes back to a multiple of itself, y goes back to a multiple of itself. Right? So these are your eigenspaces. Each of these is going to a multiple of itself. Now, what is add x doing? Okay, when add x hits y, okay, it sends it to h. So add x moves things like this. And when it hits h, it sends it to a multiple of x. When it hits x, of course, it sends it to 0. Okay. And what is add y doing? Add y, when it hits x, right? Bracket xy is h, bracket yx is minus h, sends it like this. And then y with h is a multiple of y, so it goes here, and then y with y is 0, so it goes like this. In other words, add x and add y are nilpotent, right? They're ultimately sending everything to 0. But more than that, what's interesting is that they're just shuffling the eigenspaces of add h, right? They're not doing random things. So this kind of internal structure will become very important when we look at the more general things called simple or semi-simple algebras. We will be able to replicate this sort of behavior there. In fact, SL2C will be seen to be an important building block for their behavior. So there's sort of preview of some things that you will see later with specifically algebras. Okay. All right, so I think it's approaching time to stop. All right. So maybe, sorry, I'll just take 2 minutes because I just want to mention one thing, right? I have only talked about what I call matrix groups. And the promise was to say something about Lie groups. Okay, but what's happening in a matrix group G? We have seen that there's a corresponding Lie algebra, which is a vector space. There's a close correspondence between what's happening around identity of G and zero of the Lie algebra. And this correspondence is described by the exponential map. Okay. So what does this correspondence really allow us to do? It allows us to differentiate in this neighborhood. Because this is a local homeomorphism, it means that this little neighborhood of identity in the group can actually be seen as part of Euclidean space, right? It can be seen as a part of some Rn, and you can locally do your differential calculus. Okay, then what we can do is by multiplying with group elements, we can take this neighborhood and we can move it to other parts. We can translate it around and so each part of the group will get identified with a piece of Rn, and you will be able to do calculus. So now you can actually do calculus over the entire group. I mean, because it's all local behaviors. So one of these so-called charts at a time you can do it. Okay. So that's the idea of what you can do with matrix. So what are Lie groups? Lie groups are exactly a more general, just what we have observed and stated abstractly. So what's a Lie group? It should, of course, be a group. Okay. Then it should be what's called a manifold, meaning around each point you should have a neighborhood homeomorphic to say an open ball in Rn. Okay. And so with the help of this, you can do your calculus. Whatever calculation you have to do, you express it in these coordinates and then you do it. Okay. So that's what is a right? And so again, you need to have these all over. Okay, so that's a differentiable manifold. So a Lie group in general is a group with this differentiable manifold structure. And so that the group operation and the inverse map are differentiable when you view them through these coordinates. And what we have seen basically is that matrix groups are examples of this. The exponential map provides you the coordinates that you need. Okay. All right. So I think I will leave it at that. Let me just tell you about some references where you can take these things further. Okay. All right. So a first course in representation theory and Lie groups by Bhachi, Madan, Sitaram, UB Tiwari, 2000 book, I think, Universities Press. It's a very slim book but very approachable and packs in a lot of information in what it does. So it will give you a brief look at linear groups, matrix groups, how to differentiate, integrate on linear groups, and applications to studying functions on linear groups, especially I think the SU2 example, and so a bit of harmonic analysis as well. Okay. Naively Theory by John Stilwell is kind of again another small book in this, similar to what we have done in these three lectures. Okay, so it looks again at matrix groups and the concrete things and works out various examples. It's more of a sort of example-based book in that sense. Matrix book for undergraduates by Christopher Tapp. It's one of those AMS student library books. So again, another nice introduction to matrix groups. These two are actually very nice for if you want to do anything with undergraduates, for example. So these two are very nice for introducing even a second year undergraduate student to the basic phenomena involving Lie groups and Lie algebras. Okay. This book by Rossman, Lie groups introduction, to linear groups is a much more comprehensive and higher level book. In the Lie theory, there are some sort of subtleties which may trouble one at first. In linear groups, the option is either to stick to examples where those subtleties don't crop up, which is what I have done in my 2 lectures, frankly, or I also find a good way to do it, and I think Rossman has done it in a very nice way. Okay, so he has not hidden from it, and he has hidden from them, and he has found nice ways to deal with them. Okay, so I think that is a book I would recommend very highly. Then Brian Hall, Lie groups, Lie algebras, representation. Well, this will take you to representation theory, so that is the big advantage it has over the others. Introduction to Lie algebras again, so basically I'm telling about introductory books, not the more famous, comprehensive, advanced books on Lie groups and Lie algebras. I think future speakers can tell you about those. I'm sticking to the more introductory ones. Okay, so for Lie algebras, usually one is told to read Sayre or maybe Humphreys. Okay, and this is a sort of, in some ways, a friendlier version of Humphrey's Introduction to Lie algebras by Erdmann and Wilden. Okay. So again, something that an undergraduate could read quickly. Okay. Here's a couple of things, as you go to more advanced things, they do sidestep a couple of things. But it's okay. For a first introduction, it's pretty good. And if you do want to see what are Lie groups really, not just linear Lie groups, okay, then there are many books. Most books on differential geometry will have some portion on the special case of Lie groups. I'm mentioning this just out of loyalty because it was the first book from which I learned about Lie groups. All right, but it's a very standard text. It's a bit terse, but it has a lot of information, many viewpoints. So it's a very nice book for a basic introduction to manifolds and Lie groups, book by Warner. Okay. All right, so I think I'm done. There are things I hope to say at first, which I didn't get around to, but there are also things I didn't plan to say, which I managed to say. So I think all in all, it's turned out all right. I hope that you will have learned things which will be useful for the future lectures in this series. Thank you.
Okay, thank you for such a beautiful illustration. So are there questions or comments from the audience?
I guess they're a very knowledgeable audience.
Yeah.
Okay.
Anyway, thank you once again. Devendra, you have any other comments?
No, so thanks, Samya, also for coming to share these 2 talks, and maybe we will see you later also.
Sure.
And thanks,
sure.
Professor, for this nice set of lecture. I think Samir will take over from here. He is here.
Yes, that's right.
And we will stop this now. Thanks. Happy Diwali to everyone.
Thanks, you too.
Thanks, sir, for
See you.
also introducing the Lie algebra, doing a good amount of Lie algebra actually.
I thought you are quite overbooked in terms of what you have to do in your lectures. I
Yeah,
thought I
so
better